NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everyone. My name is Gregory Smith from Jet Propulsion Laboratories Communications and Education Directorate, and I am thrilled to be your host for tonight's edition of the Von Karman series. Most of us don't realize that we utilize devices, materials, and scientific knowledge every day that was first developed for space-based missions here at NASA JPL. Tonight we'll be discussing these so-called Spinoffs, or commercialized NASA JPL technologies and expertise that benefit the general public. We'll explore how a spinoff makes its way from JPL into the world, and then do a deep dive on Carbon Mapper, the NASA-designed and built instrument at the heart of the Carbon Mapper Coalition's first two satellites. These spacecraft will pinpoint and measure methane and carbon dioxide sources in communities around the world from low Earth orbit. To wade through the multiple questions we hope to receive from you, our viewers, we have my friend and co-host, JPL Public Outreach Specialist, Rachel Zimmerman-Brockman. Hi, Rachel.
Hi, Greg. Hi, we are so excited to read all of your questions about JPL spinoffs. Our team will be working behind the scenes to pull up questions that you send us from LinkedIn, X, YouTube, and Facebook. If you're on any of those platforms and you don't see a way to ask a question, try refreshing your browser. A Q&A box should appear. At the end of tonight's presentation, I will field some of the questions that you ask to our two speakers. We won't have time to answer all of them, but we'll answer as many as we can in the time provided. We want to hear from you. This is your space program.
Thank you, Rachel. Rachel will return to moderate our Q&A later in the program, so make sure you are asking all those questions. Joining us today, we have two speakers who know a thing or two about spinoffs. First up, we have the manager of the Office of Technology Transfer here at JPL, Daniel Broderick. Hi, Dan.
Hey, Greg. Great to be here, and happy summer solstice.
Oh, happy solstice. Very good. Excellent. Excellent timing with this talk.
It is.
Next, to talk about the spin-off Carbon Mapper, we'll be speaking with JPL research technologist Dr. Andrew Thorpe. Thanks for being with us, Andrew.
Absolutely. It's a pleasure to be here and look forward to the conversation, Greg.
Excellent. We'll be back to chat with Andrew later in the program. So Dan, let's begin with you. What exactly does the Office of Technology Transfer do here at JPL?
Well, Greg, we don't want to hide our lead under a bushel. We want to get our technology out there to the public so it can benefit everyone as much as possible. So we concentrate on discussions with the commercial sector, getting it out to government sectors that can also use our technology, other government agencies besides NASA, and also to nonprofit research institutions such as universities and other foundations that can use our technology. And we're constantly providing technology to the commercial sector, government sector, nonprofits on a daily basis, and we're just trying to benefit people as much as possible with this research that JPLers are doing.
I think people may be surprised to learn that there is a thriving department here on the lab devoted to supporting spinoffs. Before we go any further, how exactly does a JPL technology or expertise become a spinoff, making its way to the general public?
Oh, that's a very good question. Well, of course, it first starts out with JPL technology. Next slide. And we take a look at that technology. And this is coming from researchers in many different areas. I was really surprised at how many different areas of research JPLers are devoted to doing. They're working in metallurgy, of course, and in software and avionics, and developing new batteries that can operate at 200, 300 degrees below zero, or 500 degrees above zero, depending on which planet you're on. We take a look at all these technologies in the technology reports that the researchers send us. And the researchers send us these on almost a daily basis, as you can imagine. And so we go over these reports. And next slide. We determine, do we want to patent this? And at this point, it's probably a good idea to go into the fact that the California Institute of Technology manages the Jet Propulsion Laboratory. And so Caltech is able to determine whether or not we want to own the patent. We are granted software copyrights to all the software that's invented here at JPL. And we look at the applications of what the technology does. And as you can imagine, there's all kinds of applications. Some of the applications are instruments, technology having to do with remote signaling, avionics, material science, signal processing, planetary protection, and software and systems. It really runs the whole gamut. I can say that we're a mile wide. We also go very, very deep on all of these technologies as well. So we got the whole dimensional system going here. Next slide. As I mentioned, we then look at the intellectual property protection. Sometimes we decide to file a patent application, and that's especially true if we think the technology is going to need investment from the private sector to commercialize. Sometimes we feel that the best thing to do is to devote it to the public. It's the best place for it. Other times we are granted copyright and we'll license the software copyrights to companies, and then we'll negotiate a license agreement if we decide to protect it with the commercial sector, or we'll do a startup company. And we've done many startup companies out of JPL, and we'll talk about some of those in a little bit later in the program.
It's quite a process. What kinds of support do we offer outside startups?
Well, as I mentioned, Caltech is able to take title to the patents, and so Caltech does provide a lot of resources to our entrepreneurs. And so it starts out by typically meeting with our entrepreneur in residence who is an entrepreneur. Her name is Julie Schoenfeld, and she worked for a JPL startup named OeWaves and sold part of the business to General Motors. So she's very sophisticated, has a Harvard MBA, knows an awful lot about doing startups and helping folks with their business plans and ideation and getting started, putting a preliminary team together to talk with investors, and then once you get those investors, putting the real company together. And as you can imagine, these are startups. Chaos rules, so there's all kinds of ways in which this happens, but that's kind of the general plan in which we go by.
This must be a long system of time investment. How long does this process usually take? Do some technologies become spin-offs faster than others?
Well, it depends, as we all like to say. Sometimes software, in particular, is fully developed here at JPL for an application, and it's so developed that we can simply license it very quickly to a company that's interested in using it. Other times, we really need to mature the technology and see if it works for new applications, and particularly commercial applications that are outside of what JPL is doing. I would say the typical time frame is anywhere from a year to 5 years before it really gets commercialized. And sometimes it takes quite a bit longer because a lot of JPL technology is way ahead of its time. And so we've got some micromechanical technology that is approaching terahertz speeds, and we've talked to folks in industry about this, and they just say, well, this is way ahead of anything that we're doing in the commercial sector, but best of luck, we'll let you know when we're ready for it. So it runs the gamut.
So you have to wait for them to catch up a little bit.
Yes, we do.
Speaking of timelines, although not strictly a spin-off of JPL Tech, in terms of speed, probably the fastest version of this process was during the pandemic when JPL engineers and scientists got together to solve the lack of viable respirators in those early days of COVID-19. They designed, tested, and received FDA approval and licensing for their vital respirator, which went from first ideation to shipping to hospitals in under 2 months, which is incredible. My colleague Nikki Wyrick hosted a terrific von Karman talk on Vital last July. If viewers would like to check out that. It's incredible story.
It is. I remember doing that, and I remember negotiating a couple dozen licenses to companies all over the world for that technology.
Amazing. Dan, what are some of your favorite spin-offs that JPL has had a hand in bringing to the public?
Well, one of my favorites is, of course, sitting on my cell phone right now. Next slide.
Mine too.
Yeah, and this is called complementary metal oxide semiconductor pixel arrays. That's a mouthful, but what it means is that back in the 1990s, I believe early 1990s, quite a while ago, some of our researchers said, hey, we need some lower power imaging technology that we can use on our satellites that won't be such a hog on power. And industry really liked this because they like the low power, but also this CMOS technology is very compatible with existing semiconductor standards and processes, and integrates very well with computer technology, existing computer technology. So they just gobble it up right away. So now this technology is used in virtually all cell phones, and it's used in digital cameras. And it's just one of these technologies that's ubiquitous, and we're going to talk about it a little bit later as well in a particular application. Next slide. And now we'll talk about the computer looking back at you and looking at your eyes, and then your eyes looking at the computer, and actually your eyes creating a cursor on the computer. Who is this good for? Of course, it's good for the disabled. And JPL collaborated with an eye tracker manufacturer to reduce the size and increase the accuracy and the portability and importantly the affordability of these eye trackers, so you can fit a relatively inexpensive device on a wheelchair that opens up our world to the disabled.
It's wonderful.
Next slide. And a lot of people know that way in the upper atmosphere we've got this thing called the ionosphere. It's basically an electron layer that can interfere with satellites that are helping airplanes navigate and land and that kind of thing. And so JPL has developed world-class ionosphere correction technology that the Federal Aviation Administration uses so that you can reach your destination safely and accurately. Next slide. And we've JPL have made that technology, GPS technology, extremely accurate. There are sensors on the tectonic plates. These plates are moving at about a fingernail width per day, or a little bit less than that. And if you're putting the sensors on those plates, you can determine location. You combine it with GPS signals, you can determine location very, very, very accurately. And 911 responders use this information to get where they want to go and to know exactly where they're at. And it can position people within really inches and even centimeters of where they're going. And so they know exactly where they are. Next slide. So in spacecraft, there are microbes. Usually they're hitching a ride from Earth, typically. We do try to clean the spacecraft as much as possible, but they're there. And especially in the ISS, we do have these air filtration systems that catch these microbes. And we bring the filters down to Earth, and we look at these microbes, and it's very fascinating to look at these microbes because they actually evolve in space. And some of these microbes have evolved to deal with UV radiation and to more effectively protect themselves from UV radiation. And we've actually used this technology to create more effective sunscreens and skin lotions that are available. Next slide. So I was at the dentist today, as a matter of fact. That is the honest God truth. And I was looking at my x-rays. Anybody that's been to the dentist lately probably knows they don't use film for x-rays anymore. They used digital imaging, and that digital imaging was an offshoot of CMOS imaging that we licensed to a company called Sirona, and now it's used ubiquitously in dental offices all over the world. And it's great technology because you don't need to use as many X-rays, so less X-ray exposure for you, less X-ray exposure for your dental technician, and the X-rays are available much faster, so that you and your dentist can look at them, like I did this afternoon, and then you can transfer the X-rays much more quickly and accurately as well. So very, very, very nice, and also CMOS imaging has found applications in digital healthcare all over the place, especially in X-rays.
Dan, I certainly hope that you let them know at the dentist office that we helped
Absolutely.
get X-rays of your teeth.
People need to know this, yes.
Sorry, next slide, I think.
And sometimes GPS is fantastic technology, but there are times, especially when you might be in a GPS-denied area where the GPS isn't working very well, or where you need to use a sensing technology for your orientation, which direction you're facing. And GPS can do this, but it's got some troubles doing that. And also where you might need to know what floor of a building you're on. And so we have a researcher here that developed a technology called magnetoquasistatics, and this technology can determine what floor you're on in a building, what position you're facing, and especially for first responders, if a first responder is down, and on the floor and needs medical attention. And so right now this has been licensed to a startup company called Balboa Geolocation, and they're working very closely with first responders, especially fire agencies, to test this and do and see what other types of applications that they can use, including other types of first responder applications. Next slide. And JPL developed some augmented reality technology to develop the Perseverance Mars rover, and fascinating technology. I remember going into the lab, and you could actually walk through the Mars Perseverance rover virtually and look at all the gears and electronics and levers and hinges and everything, the wheels that was on this. It was just fascinating to walk through. And you can also put yourself in any virtual environment that you want to as well. And of course, our favorite environment is on Mars. But it's also very, very, very good technology, and we're looking for some commercial applications for this as well. Next slide. So a lot of people don't realize we have an awful lot of satellites looking at the Earth. Even though we've got a lot of stuff going up to Mars and Venus and Jupiter, most of our satellites are actually looking down at Earth, and these satellites give us terabytes of data, just so much data that you really need to visualize it to make sense of it. And so we've developed software here at JPL for data visualization, where you're dealing with just massive amounts of very complex data. And it turns out that many companies in the commercial sector have the same issue, and other government agencies have the same issue. And nonprofit foundations that are looking at massive amounts of data have the same issue. So a company called Virtualytics was spun out and is doing very well and thriving here in Pasadena on Lake Street, last I saw. So and this has turned out to be a very successful company here in Pasadena. Next slide. And another spin-out company called Advanced Telesensors has developed technology. It's technology for its microwave technology, and they can sense your heart rate, your breathing, and sleeping with no contact, no physical contact, no electrodes, nothing to hold on to. And this is now being tested in nursing homes, so the patients can be monitored all night and get their heart rate and breathing and tracking other vital signs, so they can make sure that they're doing well and healthy, and if they need anything, that they can set off an alarm and have somebody come help them. And this could actually find your way into your home as well, because we're looking for other applications as well. Next slide. So JPL has developed a number of methane sensing technologies, and we're going to talk about that a little bit further. One of the methane sensing technologies was used on the Perseverance and Curiosity rovers. And the general technology it was a laser technology, open path laser spectrometer technology that was able to detect very, very small amounts of methane. And it actually discovered methane on the Gale crater on Mars and elsewhere. So there is methane on Mars. And this technology was then reduced in size and reduced in cost to the point where you can put it on a unstaffed aerial vehicle. And which is fantastic, because now we've got another company called Spinoffs that is putting these methane gas sensors on UAVs that are then monitoring plants. They're monitoring landfills, pipelines that might have leaks, and other natural sources of methane. And as you might know, methane is a very nasty greenhouse gas, very, very much more potent on a per molecule basis than carbon dioxide is. And Andrew can probably talk more about that. And so this has been a very important spin-out technology, and it is now being used all over the world. The last time I talked to the CEO of this company, Spinoffs, and I was surprised at how widely this technology is now being disseminated. They're working with people. They're working on all 5 continents, and they've got all kinds of deals with companies that are using this technology to determine methane leaks and sensing, and it's just a wonderful technology for the environment and for even finding methane as well.
Fantastic.
Next slide. So as a foray into our next speaker, we've got a couple of other technologies that can do methane and carbon dioxide sensing. Avarice, which is on the airplane on the right, is still being used on airplanes, and that's uses diffraction. As you might remember from your science class, that's when light hits an edge and it gets sent in a little direction in an angle, and it gets picked up, and by that angle you can figure out what wavelength it is. And so Avarice is using very, very complex diffraction sensors that are in airplanes right now, and Andrew's going to talk about how we're going to up that game. And we've also got spectrometers on the ISS that's also looking at methane. And so with that, I'll let Greg introduce our next speaker.
It's an incredible list, and I know it only touches on a tiny fraction of the number of spin-offs JPL has been a part of in our long past. We have the NASA spin-off website URL posted below. So folks should be able to check that out to learn a little more. Now, thank you so much, Dan. We'll be back chatting with Dan again later in the talk. For now, let us bring Dr. Andrew Thorpe into the conversation to talk about Carbon Mapper. Welcome back, Andrew.
Hey, Greg.
Now, research technologist Dr. Andrew Thorpe, what exactly does a research technologist do?
That's a great question, and it's a sort of a complicated job title, right? So a research technologist basically is trying to work with existing technology and also develop future technologies that can answer scientific questions. And for the last 10 years or so, I've been pushing technologies that can allow us to map greenhouse gases in a better way.
Great. Before we dive into what makes Carbon Mapper tick, we should probably explain what imaging spectroscopy is and how it works, yes?
Absolutely. And I think we've got a slide that gives a nice description of how this technology, this JPL technology, does in fact work. What we're showing in this image here is the sun sending photons down through the atmosphere. It's interacting with the atmosphere, hitting the ground, up to our imaging spectrometer that's built at the Jet Propulsion Laboratory. And the spectrometer itself measures different wavelengths of light from the visible through the shortwave infrared. and it allows us to generate these spectral fingerprints for diagnostic surface and atmospheric components. And we've got on the next slide a zoom in of that figure just to give you a sense for some of these diagnostic spectral fingerprints from things like water, soil, and vegetation. You can see in different colors. The radiance, measured radiance is at different wavelengths from the visible around 300 nanometers all the way through the shortwave infrared around 2500 nanometers. The focus of this discussion is really on the gas absorption features that are present for carbon dioxide between 1500 and 1700 nanometers and around 2000 nanometers, as well as methane that has stronger absorptions between 2200 and 2500 nanometers. And it is these gas absorption features that make methane and CO2 greenhouse gases. It absorbs photons and causes global warming and greenhouse gas warming.
Historically, how has JPL spacecraft utilized imaging spectroscopy to study the universe?
So we have a long track record of developing this technology. If we go to the next slide, you can see a few examples of some of the Earth observations. The first spectrometer that was built at the Jet Propulsion Laboratories AIS back in 1984. We followed that with the Airborne Visible Infrared Imaging Spectrometer, AVIRIS. We're very good at JPL of having acronyms, long acronyms at that. So this is a long one there. Then this is a very large instrument. You see that in the center upper panel with a person for scale. AVIRIS has been used for a number of different science applications, both to characterize the surface as well as the atmosphere. And sort of a notable use for AVIRIS was that after the September 11th, Twin Tower sort of catastrophe, we had AVIRIS actually characterize the spectra of that location after that event. Since then, we've been continuing to build better instruments, smaller and higher performing instruments. And you can see the AVIRIS next generation instrument, much smaller. There's another person for scale in a bunny suit. Then followed by the snow and water imaging spectrometer with a hand for scale, so smaller, even smaller. And then what I'm showing in the final two panels there are the spaceborne versions of these types of instruments, the first being the Earth Surface Mineral Dust Source Investigation called EMIT, and I'll be showing some results from that later today. And then the Carbon Mapper set of instruments. There are two instruments. They will be Tanager-1 and Tanager-2 from in space later this year.
Am I correct in saying we have a long history of creating greenhouse gas mapping using this type of instrument?
Absolutely, we do. But in addition to that, we have characterized with imaging spectrometers the planetary surfaces as well. So if we go to the next slide, you can see a few examples of some of those observations, including Mars, the Compact Reconnaissance Imaging Spectrometer, CRISM, and M-Cubed, the Moon Mineralogy Mapper, that was used to identify frozen water at the poles of the moon. And that instrument is not active, but it is orbiting the moon currently. And then finally, we've got MISE, the instrument that is going to be going to Europa in the future. If we go to the next slide, I can talk a little bit about the sort of greenhouse gas application. I've been involved in that since I was at graduate school at UC Santa Barbara. Began by publishing papers that demonstrated, as you see in the upper left there, the first set of observations, maybe the second set. My dissertation advisor did the first paper. I'll give him credit for that, but followed on with a second paper just showing that we could do this over the ocean as well as over land areas for both natural and anthropogenic emissions. And then since then, over a decade or so, we've been really trying to push the science forward. What I'm showing in the center panel there is the first methane point source that was observed from space using the Hyperion satellite by colleague David Thompson at the Jet Propulsion Laboratory. Airborne campaigns, we've done a number of those over the years. This is an AVIRIS Next Gen campaign from the California Methane Survey when Riley Duran was the PI. He's currently the CEO of Carbon Mapper, but he was at JPL at the time. And then since then, we've been launching instruments into space like EMIT, and showing that we can map both methane and CO2 point sources from space, and also using next generation airborne instruments like AVERIS-3 to characterize methane emissions. This is a nice example from Dairy Waste Lagoon. If we go to the next slide, I can talk a little bit about how these instruments work and how we measure these greenhouse gases. So we call this type of instrument a push broom scanner. The idea being that think about pushing a push broom over the sidewalk. It scans over the surface of the Earth, measuring different wavelengths of light from the visible through the shortwave infrared over 400 channels in this example, and that's visualized as that data cube that you see in the vertical direction. And EMIT provides an 80-kilometer wide image swath with a 60-meter spatial resolution, which is really critical for mapping out methane and CO2 point sources. The spectral fingerprints themselves are shown on the next slide for methane, and you can see some strong absorption features between 2200 and 2500 nanometers, as measured by our instrument in purple, and it matches nicely with some modeled results that we have. And it is these absorption features that make methane a greenhouse gas, but also allows us to generate imagery like I'm showing on the right there for this methane emission from a landfill. So for each image pixel within the scene, we can estimate a concentration enhancement, and we can use that to estimate an emission rate from this example. For CO2, we also have spectral fingerprints as shown on the next slide for 3 pronounced absorption features that are shown in that figure. And that allows us to do a similar type of emission quantification for power plants and other large CO2 sources. And these are 2 examples of coal-fired power plants in China. If we go to the next slide, this is a sort of a video that shows all of the methane plumes that were observed with EMIT on board the ISS since launch.
Wow.
And what's pretty remarkable is that you start to see distributions of these plumes in different areas. I will note that we don't have full coverage here because the primary mission of EMIT was really to focus on arid regions. So when we first started the mission, we were really focused on those arid regions. Since then, we've expanded our targeted areas, and we are getting coverage over much of the globe, and we're starting to see more and more methane plumes in these different areas. So Carbon Mapper will be sort of building off of this success and launching 2 instruments to do this type of work in an even better way with improved sensitivity and improved repeatability over time, and I'm really excited about the Carbon Mapper program.
That graphic is really stunning in that it's hard to not to see that the correlation between the findings and areas of great population. Am I correct in that?
Yeah, there's definitely a correlation to some degree with population. There's also, I would probably argue, a more of a correlation with oil and gas production areas in particular. So if you were to zoom in the United States, you would see kind of a cluster of methane plumes in Texas, in the Permian Basin, which is the largest oil and gas producing basin in the United States. Similarly, there's Turkmenistan is an area that has a lot of methane plumes, and you would see that. But absolutely, there is a relationship to population centers as well.
If any of our viewers would like to do a deeper dive into EMIT, we hosted a terrific von Karman talk on this subject last April that I invite you all to check out. Now, Andrew, let's chat about the incredible Spinoff Carbon Mapper. First off, what is the Carbon Mapper Coalition?
Absolutely. So let's go to the next slide, and I'll sort of walk through the Carbon Mapper Coalition. The mission itself, Carbon Mapper is a nonprofit that delivers actionable and localized methane and CO2 data products. And the Carbon Mapper is at the forefront in terms of the integration and organization. So they have put together this unique coalition of private and public sector actors with expertise and resources to deploy a science-driven, sustained, and operational decision support service for maximum impact. And they've been working with a diverse set of stakeholders and individuals that are in this figure. If we go to the technology side of things, that's where I'm most involved. The Jet Propulsion Laboratory imaging spectrometers are the core to that technology. JPL built one of the two instruments and worked very closely with Planet, who built the second instrument. Planet is launching those instruments into space after integrating them into their satellite buses, and will be doing the operations on a daily basis. For the science, this is being led by Arizona State University and the University of Arizona, in addition to additional organizations. Next, we have the policy side of things. So again, this is really a mission that's really driving to have policy relevant results. And to do so, Carbon Mapper is working very closely with the California Air Resources Board, as well as the Rocky Mountain Institute and others. And then finally, this project is funded through philanthropy, and that includes the High Tide Foundation, the Grantham Foundation, as well as Bloomberg Philanthropies.
JPL is involved with building one of these instruments. Can you talk, Andrew, a little bit about how Carbon Mapper was created?
Absolutely, and I think I have a nice slide that will talk a little bit about what we've been doing for some time at JPL to support Carbon Mapper, and that is namely to build the imaging spectrometer that will be going into space later this year. This is one of the two instruments. This was the instrument that was built at the Jet Propulsion Laboratory. On the left, I'm showing the imaging spectrometer, that gold surface there. It's about 22 centimeters in height, and you can see three different bipods sort of in a silver color there that are at the top of the spectrometer. Those bipods are used to get the spectrometer attached to the much larger telescope, and you can see that telescope in the figure on the right, that sort of black mass with that sort of aperture for the telescope. So those get mated together, and lots of electronics and other pieces of equipment and used to make that happen. So that's sort of the first set of images. If we go to the next slide, you can see some of the testing that we did at the Jet Propulsion Laboratory, and this is an example where we actually used the spectrometer to measure methane for the first time, and we used a gas cell with methane in it, and basically passed light through that cell, causing absorption features, and then that signal gets measured by the detector array. And this is an example of those characteristic spectral fingerprints for methane. Particularly, a very strong one is visible there from 2200 to 2400 nanometers, a series of them. But if you look really carefully, there's also a weaker set of absorption features around 1600 nanometers, and that is expected as well. So this was a nice example of just measuring methane in the laboratory for the first time before it goes to space, and when it will be doing this in an operational sense. If we go to the next slide, thank you, we've got an image of sort of the completed instrument, I guess from the JPL perspective, before it was delivered to Planet, where it will be integrated into their bus and ultimately launched and operated. So there's a whole very large team of engineers and other folks that are involved in this, and this is just a picture showing 4 of those folks getting ready to get the instrument delivered to Planet, and it was delivered a few weeks back.
This is a good example of a spinoff that isn't personally owned by the public, but greatly benefits the public. How will Carbon Mapper's findings affect real change in communities around the world?
Yep, that is really the core of Carbon Mapper's ethos for being, right, is to deliver actionable information on methane and CO2 emissions. The next image or animation, I would say, is a nice example of sort of how this will work. This is the Permian Basin in Texas, the largest oil and gas operating basin in the United States. And what this image or this video will show is 2 different instruments, the Tanager-1 and Tanager-2 imaging spectrometers, passing over the area providing wall-to-wall mapping. So this is Tanager, the first Tanager instrument, Tanager-1, coming into frame, and you can see the coverage of the Permian Basin, and what it will deliver is point sources within that image swath. Tanager-2 will pass and continue to mow the lawn, and you can see that example in the next pass with different point sources of methane in this example shown. By having two different instruments up in space allows for improved coverage of this example, this Permian Basin, but also Carbon Mapper is going to be focusing on areas of interest for both methane and CO2 mapping in a global sense, and this is really enabled by the two satellite instruments.
Incredible. Thank you, Andrew and the Carbon Mapper team, on what promises to be a profoundly important spinoff to advance new data-driven emission mitigation strategies. It's incredible. And we wish you all the luck. I think we should bring Dan Broderick back as we turn to my co-host, Rachel. Rachel, I imagine you have a ton of questions for our two guests. What have you got for us?
I do have some questions that have come in. The first one is Francine on LinkedIn, who asks, are there any spin-off technologies that JPL has developed that would help spacecraft navigate around the moon?
Yes, we have quite a few. One of our technologies is called Monte, M-O-N-T-E, and it's a flight planning technology that we are licensing to other companies, including Blue Origin and Amazon Kuiper and a host of others. And it helps you plan your flight and plan how you're going to get to your destination. And we also have a host of landing technologies. As you can imagine, we've landed on Mars so many times, and it's very difficult because it's 7 minutes. The radio signal takes 7 minutes to get there on a good day. And so everything has to be automated. You can't use a joystick, or you can't, control things. You have to land autonomously. So we have a lot of landing software as well, and we've licensed some of our landing software to private companies that are using it for lunar or other missions.
Yeah, great. Thanks so much for answering that question. The next one is from Paul Johnson on YouTube, who asks, can imaging spectrometers be used for the sun, or is that not an option?
Andrew, I'll let you take that.
I'm happy to say that, to answer that one. So absolutely, spectrometers have been used to characterize, stars. Each one is individually tailored for the task, right? So the instrument that I was describing and for looking at the Earth for greenhouse gases won't be the right instrument to point at the sun, but folks have developed imaging spectrometers and spectrometers in general to characterize the stars and planets as well, for sure.
Great, thanks. The next question is from Natalie Watson on YouTube, who asks, first of all, it says, great technology. And then she asks, how do you integrate nanotechnology with the collection of samples from the moon and Mars?
You stumped the panel.
That's it.
Well, one thing that we can do is we can look at, we don't have any samples from Mars, I'm sorry to say. We're working on a Mars sample return mission, and we do hope that that's going to be get funded and it's going to be a successful mission. But in terms of lunar samples, we have lunar samples, and we in fact have some lunar samples in the von Karman Museum here at JPL. And some of the lunar samples have been looked at for minerals and for possible signs of life, which have been found, and for other purposes as well. And typically, you're looking at these lunar samples using very high microscopy, and you're trying to find what is in those lunar samples that can indicate the evolution of the moon and the characteristics of the moon, and perhaps if there are what kind of minerals and elements there are on the moon that might be valuable and might be worth researching.
Great, thanks so much. Let's see. Wes on Facebook asks, MRI and CAT scans owe their origins to image processing technology from NASA Spinoffs 2, if I'm not mistaken. So the question is, there's kind of a difference between JPL technology and NASA as a whole technology. I'm not sure kind of what the delineation there is as to whether this was NASA technology or JPL technology or a combination of the two or somebody else.
I see. Well, I can answer that a little bit. I do know that MRI technology was actually developed in Scotland at the University of Aberdeen initially, and there were some Nobel Prize winners who received the Nobel Prize, and I believe they were Scottish researchers. I do know that some NASA technology was used in terms of the image processing for medical images, including CAT scans and possibly MRI scans as well. So typically, there's the old story, you see so far because you stand on the shoulders of giants. Usually when you look at technologies that are in use every day, you realize that there are, dozens or hundreds of contributors to that technology that's now being used. And that's very true. And in terms of the technologies that I talked about on CMOS imaging, for example, we handed that off to several companies that did tremendous work on getting it to work and getting it to actually work in your cell phones and cameras and instruments. But in terms of NASA versus JPL, NASA is just one space center, and there's 8 other space centers, and we sometimes cooperate and collaborate and come up with new technology together, and sometimes it's new technology that JPLers come up with on their own. So there's a host of things that are going on between JPL researchers working, in groups here at JPL, and then also working cooperatively and collaboratively with other JPL centers, and even with other government agencies. We do quite a bit of work with the Department of Energy and then all kinds of agencies that can benefit from what we have, or from our resources and from our researchers.
Yeah, speaking of other federal agencies, Bill on X asks, I thought Global Positioning Systems, or GPS, was proposed, designed, created, and operated by the U.S. Department of Defense. In what sense can GPS be described as NASA technology?
Yeah, good question. So again, you see so far because you stand on the shoulders of giants. So we took that the GPS technology, and then used what we could to do precise orbit determination. So if you send a spacecraft up and you want to make sure that it's on track, we've developed some fantastic technology that is used in spacecrafts all over the world for that. It's called GIPSY, and you can look that up on our website. GIPSY, I believe, is what you look at. And in terms of what I mentioned for GD GPS, that's Global Differential GPS. And so JPL has developed that technology. Other private companies have developed that technology as well. And that's when you're taking the GPS signals that are already up there, and you're adding additional information to make it more precise. And there's a lot of ways that you can do this. One is to use cell phone towers signals and do triangulation. That's one way you can increase the accuracy. Another way is, of course, as I mentioned, where you get the most accuracy using the sensors on the tectonic plates. So this is really taking the existing GPS network and then doing something with it, for spacecraft or for emergency responders, et cetera.
Cool. Peter Kojic on YouTube asks, would there be something like GPS on the moon for upcoming astronaut expeditions and that sort of thing?
My understanding is that you can use GPS on the moon, but we're developing technologies that work on the moon that might be in GPS-denied areas. It's a good question. Spacecrafts use GPS all the time for precise orbit determination. I don't see why it can't be used on the moon as well, but I can imagine the GPS signals being blocked in certain areas on the moon, and that's why we're developing some of the GPS-denied technologies.
Okay, I know you spent a lot of time at the beginning of the talk talking about like some of the examples of JPL technology, but NDU192 on YouTube asks, what technologies that JPL and NASA are developing have the potential for impacting the most people on Earth? And what about potentially impacting typical daily life? And we've given some great examples of sunscreen and dental imaging and the cameras in your cell phone, but are there any other things that come to mind as like really good examples of JPL technology that could impact your daily life?
Yes, we do have some other examples as well. I use, of course, the short list, given the limited amount of time that we have. But one thing I do want to mention is that typically the technologies that we're getting into my office and that I'm licensing to companies are actually industrial technologies. It's companies that it's technologies that companies are using for their processes or for spacecrafts that may be incorporated into the products that you're using, but it's a little bit upstream from what you're actually seeing in your product. You may not see it right away, but as we move forward, yes, of course, we're going to see additional technologies making the way into consumer products as well. But I would say that typically the typical technology that JPL produces is not really supposed to go into consumer products. They're supposed to go into to help us do space missions. And every once in a while, these technologies do find their way into consumer products, such as cell phone cameras and medical imaging and dental imaging and sunscreens and et cetera, the things that, and FAA, the Federal Aviation Administration is using these signals to correct for the ionosphere for aircraft, and I should say Japan is using our technology for this as well. So a lot of times we do have technologies that really help people here on Earth and also in space.
If I may,
Great, thanks so much.
The technologies that Andrew is working on have the potential to benefit humanity across the globe.
Absolutely, and thank you for mentioning that. I think maybe not front of mind for daily life when it comes to things like sunscreen, but really well said. I think these technologies are relatively young. It's about 10 years or so, and what we have been seeing with technologies like EMIT and undoubtedly what Carbon Mapper is going to be able to do and future technologies is, by identifying greenhouse gas emissions of methane and CO2, there's the great potential to offer not only a greater understanding of how greenhouse gases impact climate, but also the potential for direct mitigation, right? And I think that's a concern for a lot of folks, trying to figure out how we can reduce greenhouse gas emissions. I think these technologies make what is invisible to our eyes very visible, and we can quantify them. And ultimately, by sharing these results with folks that want to do something useful with it, we can actually inform sort of policy when it comes to emission mitigation and such. And that's really going to be what Carbon Mapper is really focusing on going forward.
And we want to make sure we've just put up a slide which has the Carbon Mapper URL on it, so people can do a little more research on the product and the technology themselves.
So, Greg, do we have time for one more question?
I think we have time for one more question.
Wonderful. Carrie on LinkedIn asks, how did you get into a career with NASA and JPL? Do you have any advice for students who dream of working there?
I'll go ahead and start with that one. I think people come to JPL in all sorts of different paths. For me, I never thought I would end up at JPL. I just happened in graduate school to be working with a professor that worked with data from Avarice and was looped in to the methane-related work. That led to some funding that was made available through JPL, through my institution, Santa Barbara, UC Santa Barbara. And then ultimately, because sort of the field continued to grow, there was an opportunity for me to get hired in the engineering side of things at JPL. Even though I'm not an engineer, I am a research technologist and I'm working with engineers. I'm also working on the science side. So I would say, if you're interested in a particular aspect of science, wherever you are in your educational journey, right? You just go for it. You look for opportunities to maybe do internships at JPL, or just look for opportunities to work with people that are working with JPL data, and you never know where you'll end up, I guess.
And I can say that my path was a little bit different, but I was working at Caltech, and I started working on some JPL projects, and I really enjoyed working on the JPL projects. And when I was working on these projects, people had confidence in me, and I had confidence in them. And I was asked if I wanted to lead the office here, and I said yes, largely because I really like the culture here. The people are fantastic and smart and good to work with, and very just one of the best team cultures I've ever worked in. So it's just a wonderful place here.
Hear, hear. Thank you so much, Rachel, and thanks to all of our viewers for those terrific questions. Well, my friends, I'm afraid that is all the time we have tonight. I'd like to thank our special guest speakers, Dan and Andrew, for sharing your expertise and passion with all of us. Thanks to the many JPLers who took the time to help me prepare for this talk. To my wonderful co-host, Rachel, for sifting through all of those fantastic questions. Our amazing social media team for juggling our online presence behind the scenes. Our incredible audio-visual team for making all of this happen. And especially thanks to all of you for being passionate about NASA JPL's work and for tuning in tonight. Be sure to join us for next month's Von Karman talk as we celebrate our next generation of lunar rovers called Cadre. For now, remember, this is your space program, so be involved, stay curious, and hooray for science. Good night, everyone.